Hello, this is Professor Roman. Let us continue the ring theory lectures. We are ready now to talk about Chapter 5, unique factorization domains and Euclidean domains. And we'll begin with unique factorization domains. Integral domains in which every non-zero non-unit can be written as a product of irreducible elements are quite special. And that is especially true when the products are essentially unique. And to examine this further, we need some convenient terminology. So, let R be an integral domain. I'm going to refer to a factorization of a non-zero non-unit element, A, in this form where each x sub I, each factor, is irreducible, simply as an irreducible factorization of A. Such a factorization is an essentially unique irreducible factorization if whenever A has two irreducible factorizations, then n has to equal m so that there are the same number of factors, and after a suitable reindexing, xi is an associate of yi for all I. That's what it means to say that A has an essentially unique irreducible factorization. The terminology here is a little cumbersome. One of the reasons is that irreducible is a 5-syllable word. Fairly soon we're going to be able to replace irreducible by prime, and that will make this flow a little more smoothly. Essentially unique prime factorization doesn't sound nearly as bad as essentially unique irreducible factorization. Anyway, so if A has an essentially unique irreducible factorization, and we do the reindexing, then there are units, y sub I, for which yi equals ui xi, which means we can, in this factorization, replace the y's by x's, gather all the units in the front. Well, we already know that A is this product of x1 through xn, so the product of the units is going to have to be 1. So we can say all this in more informal terms as follows. When A has an essentially unique irreducible factorization, we can get all of the irreducible factorizations of A by factoring the identity element into a product of units, and then just sprinkling those units among the x1 through xn. And we'll get associates, a product of elements that are associates of x1 through xn. Given an irreducible factorization of A, we can also gather together factors that are associates. So for example, take this irreducible factorization here. Suppose that x1 and x3 are associates. So x3 is ux1 for a unit u. Then we can replace x3 by ux1, and now the factorization looks like this. We got this unit factor, but now we have x1 squared and no x3 factor. And if we continue this, scanning for elements that are associates, we eventually will get something that looks like a nice, neat factorization. U times x1 to the e1 through xm to the em. U is a unit, the exponents are non-negative, and each xi is irreducible, and the xi's are non-associates. So I'm going to refer to that factorization as a non-associate irreducible factorization. And the elements x1 through xm as the base irreducibles. For convenience, as we'll see later, I'm allowing exponents to be 0. That wouldn't happen in this factorization, but I want to also allow the existence of factors with a 0 exponent. For one thing, this will allow non-zero units to have non-associate irreducible factorizations. A unit does not have an irreducible factorization. So that's a slight advantage, but there are other advantages that we'll encounter in a few minutes. And as another convenience, for the rest of this discussion of unique factorization domains, U and V will represent units, and I won't comment on that again necessarily. Essential uniqueness can also be described in terms of the non-associate irreducible factorizations. An element has an essentially unique irreducible factorization if and only if for any two non-associate factorizations m equals n, and again after suitable reindexing xi and yi are associates, but also the exponents are the same, ei equals fi. So that's just another way to say exactly what we said before. Okay. As an example, in the integers, the integer 120 has an essentially unique non-associate irreducible factorization because these are the only irreducible, non-associate irreducible factorizations. We basically take this one where all the factors are positive, 2 cubed times 3 times 5, and we sprinkle units. But the product of the units has to be 1, so we can sprinkle 2 negative signs wherever we want. Okay. Actually, in this case, we're sprinkling 4 negative signs. And 4 negative signs here, but only 2 negative signs here. Okay. Now, with this terminology out of the way, I know it's a little cumbersome, but I think that's necessary terminology. We can define unique factorization domain. An integral domain R has the factorization property if every non-zero non-unit has an irreducible factorization. We've seen, I'll mention this again later, that there are integral domains where there are no irreducible elements, so there can't very well be any irreducible factorizations. An integral domain R is a factorization domain, sometimes abbreviated FD, if it has the factorization property. A factorization domain is a unique factorization domain, often abbreviated UFD, if every element of R has an essentially unique non-associate irreducible factors, or just, I don't even need this word here, an essentially unique irreducible factorization. Okay. So I'm a little ambivalent, but I suppose I could remove that word. Okay. The following fact is going to prove useful, and it's essentially the reason why I'm allowing 0 exponents in the concept of a non-associate irreducible factorization. So let R be a UFD. Any two non-zero elements have non-associate irreducible factorizations that use the same set of base irreducibles. And I've said here U and V are units. We're assuming that. The RIs are non-associate irreducible elements, and the exponents are non-negative integers. I'm going to let you ponder this theorem if one or both of A and B are units. It's just a one-liner in that case. But let's consider the case where they're not units. It's not terribly difficult, but it's a little bit unpleasant to write it all out. Suppose that A and B have non-associate irreducible factorizations given here. We need to scan the P's and the Q's for associate pairs. So if QI is an associate of PJ, then QI can be written as UIJ PJ, where UIJ is a unit, and we can replace QI to the FI by this product. And that can be repeated until we finally have changed. The factorization of A remains the same, and I missed a U here. B is the factorization of B now looks like this. We can gather together the units UIJ, call it their product V. We've changed the Q's to P's, same exponent, and these Q's were not associates of any of the P's. Then we can augment both of these by tossing in for A, these latter Q's here to the 0 power, and for B, we toss in the latter P's to the 0 power. So now this has base irreducibles P1 through Pn, Qs plus 1 through Qm. This is P1 again through Pn, and Qs plus 1 to Qm. So the same base irreducibles. Now comes a bit of good news, since, as we will see shortly, unique factorization domains have the property that an element is irreducible if and only if it's prime. Everything we've said so far, we can replace irreducible, the word irreducible, by the word prime, and it makes the language flow more easily. Example 4.9 shows that an integral domain need not be a factorization domain. I just mentioned that earlier, because it need not have any irreducible elements. Example 4.6 showed that factorizations need not be essentially unique. Irreducible factorizations, I guess I should say, need not be essentially unique. If we take another look at example 4.6, we can learn some more. This was the quadratic domain, and this was the quadratic norm. It's the square of the complex norm. This norm can be used to show that this domain is in fact a factorization domain, and it's quite easy. If R is not a factorization domain, then among all the non-zero non-units of R that are not the product of one or more irreducibles, we can choose one, call it A, that has smallest norm. Now we have a problem. A, therefore, has a non-trivial factorization because it's not irreducible. And since this is a non-trivial factorization, the norm of x is less than the norm of a, norm of y is less than norm of a. Therefore, both x and y are the product of irreducible elements, and therefore so is a. Contradiction. So R does not have any non-zero non-units that cannot be factored into a product of irreducibles. In other words, it's a factorization domain. But again, as we mentioned earlier, in example 4.6, we have these two factorizations of the number 21, and there are no associate pairs here. So these are essentially distinct factorizations of 21. And so R is not a unique factorization domain. It's an FD, but not a UFD. In the matter of uniqueness, we have the following result. And let's recall that an IPD is an integral domain in which the concepts of irreducibility and primeness are equivalent. I believe I called it an IEP domain before. And I didn't want to redo that lecture, but I decided, just for that, but I decided this might be a better designation. It falls more in line with UFD, unique factorization domain, irreducible equivalent to prime domain. I'm not crazy about it, but at least it conveys the message. So, theorem, let R be an IP domain. If an element A has an irreducible factorization, then A has an essentially unique irreducible factorization. Probably could have said that a little more smoothly. Every element that has a unique factorization has an essentially unique factorization. Anyway, doesn't matter. So an IPD that's also an FD is in fact a UFD. IPD and FD is UFD. I don't like this alphabet soup, but these, to use the words here, makes it quite long, so at least it does serve a purpose here. The one I really hate is this one, WLOG, okay, without loss of generality. I never use this one. I'm using these because it's just kind of more than convenient. Okay, as to proof, suppose that R, an element R, has two irreducible factorizations. Well, the xi's are prime. They're irreducible, therefore prime, in an IPD. And so xi divides this product, therefore it divides, let's say, yj. But both xi and yj are irreducible, so the only way xi can divide yj is if they are associates. By reindexing, we can assume x1 is an associate of y1. We can cancel and have this relationship. This is an associate relationship because a unit may have been introduced here. Continuing in this way, we've got to run out of factors on both sides at the same time, unless we get 1 as a product of irreducibles, which is not possible. So k equals n. After the reindexing, xi is an associate of yi for all I. We have essential uniqueness. So, what is the relationship between UFDs, IPDs, and GCD domains? Well, corollary 428, that was a corollary to Euler's lemma, told us that a GCD domain is an IPD. It's also true, we'll prove next, that a UFD is a GCD domain. I really don't like this alphabet soup. Okay, here is the theorem. Let R be a unique factorization domain, and let A and B be non-zero non-units with non-associate irreducible factorizations. Then the following hold. A divides B if and only if, as you would expect, EI is less than or equal to FI for all I. And therefore, A and B have greatest common divisor, x1 to the minimum of the two exponents, all the way through to xn to the minimum of the two exponents. Call that D. And least common multiple looks like this, which is the maximum of the exponents. So every pair of elements non-zero non-units has a GCD, and so does every pair of elements, then non-zero elements, and so we have a GCD domain. As for part one, it's certainly clear that if EI is less than or equal to FI, then A divides B. For the converse, suppose that A divides B. So B is C times A for some element C. If one of the exponents EK was bigger than FK, you could factor from both sides of this expression xk to the fk. Now xk divides this side because A has a factor xk to the ek, so there's still at least one xk floating around over here, but none over here. And we now have a contradiction. Xk divides this side but does not divide that side. So EI must be less than or equal to FI for all I. And I'm going to leave it for you to contemplate parts 2 and 3. The proof is rather short, as you can see. So, we have shown then that a UFD is a GCD domain, which in turn is an IPD. Unique factorization implies existence of greatest common divisors, which implies that irreducible and prime are equivalent concepts. As for the converses, you can't really expect that an IPD or GCD domain necessarily has any sort of factorization property. But if we toss in factorization, then things are different. So let R be an integral domain. The following are equivalent. R is a UFD, R is an FD and a GCD domain. R is an FD and an IPD. And so it looks like this. And the proof we've essentially already done. It's a matter of gathering together various results we've already looked at, so I'll leave that for you to think about. Finally, principal ideal domains are also unique factorization domains. And the proof of this fact stems from a simple observation concerning principal ideal domains. A principal ideal domain cannot have a strictly increasing infinite sequence of ideals. So if we have a non-decreasing sequence of ideals, then at some point, for some I, we must have equality from then on. It follows from that a principal ideal domain cannot have an infinitely descending, strictly descending sequence of elements, each of which properly divides the next element in the sequence. So if we have this situation, which goes to the left indefinitely, these cannot all be proper divisibility. So there's an index I for which xi equals xj. Actually, they could be associates. They must be associates from some point on, back towards the left. The proof goes as follows. If we take the union of these ideals, in general, the union of ideals is not an ideal, but the union of a non-increasing, this is a chain of ideals, is an ideal, and I'll let you prove that. Therefore, it's principal, so it's generated by an element y. Now, y has to belong to one of these ideals, and once y is in one of these ideals, the ideal is u, and from then on, you're not getting any bigger than the union, so all of the ideals after that are equal to u. This fact makes it relatively easy to prove that a principal ideal domain is a unique factorization domain. And so let's just, for convenience, temporarily say that a non-zero non-unit is bad if it doesn't have a prime factorization. Now, bad elements then are not prime, they're not irreducible, they can be factored in a non-trivial way. X is y times z, where y and z are non-units, so they properly divide x. But at least one of y or z has to be bad, because if they're both products of primes, then so is x, which we are assuming is not the case. So if R has a bad element, x naught, then x naught has a bad proper divisor, x1, which in turn has a bad proper divisor, x2, and so on, and we contradicted the previous theorem. So R cannot have any bad elements, and so it's a factorization domain. But principal ideal domains are also GCD domains that we proved in Chapter 4. So R is a unique factorization domain.